Okay, so I'm really pleased that we have Molly Gallahue from Northwestern University. She got her master's in geology and mathematics from St. Norbert College in Wisconsin. And she's currently a fifth-year doctoral student at Northwestern and will be graduating in a few months, both with a PhD and also a master's in statistics that she's picked up along the way. Her research interests are seismic hazards, seismology, and plate tectonics. She currently has 5 published papers, 2 of which are first author, and there are 2 others that are in review, and she's the first author of both. She's had outstanding student presentations, both at GSA and AGU, and is the student representative for GSA's Geophysics and Geodynamics division. In addition, she's gotten an outstanding graduate teaching assistant award from Northwestern's Earth and Planetary Science Department. She also is a co-PI on AGU's Centennial Grant for interviewing people who experienced the 1992 and 93 Mojave Desert earthquakes. And the purpose was to interview people to estimate the intensity data of shaking in California. And this was before the USGS, United States Geologic Survey, started their Did You Feel It program. The title of the talk today is Exploring the Discrepancies Between Seismic Hazard Maps for California and Historic Shaking Observations. So Molly, all yours.
Thank you. Let me get my screen share. All right, hopefully this is working. Yeah, and thank you for that introduction, Carol. I really appreciate all of that. I don't want to misspeak, so I'll just say I got my bachelor's at St. Norbert. I don't have a master's yet, but as Carol said, that'll hopefully be part of the PhD as I'm finishing up. But yeah, so I'm excited to speak to you all today. And today I'm going to be talking about some research that's pretty central to my PhD thesis. And throughout the time that I've been at Northwestern, I've really been looking at seismic hazard maps and how those compare to historic shaking observations and what causes the discrepancies between the maps, which are the predictions, and the observations. And so that's what I'm going to be talking about a bit today. We'll really be focusing on California, but these results are applicable globally, as I'll get into in a little bit. So before we get started, I obviously want to highlight that seismology has been kind of in the news lately this week. As we're all aware, a very large 7.8 earthquake hit Turkey and Syria. And this headline is from a couple days ago. Obviously, it's become much more grim since then. What's happening in this region is that Turkey, which sits on the Anatolian plate, is kind of getting squeezed out like a watermelon as the Arabian plate moves forward and into the Eurasian plate and kind of pinches that out. And as a result, we have this fault line right here, the East Anatolian Fault. It's a strike-slip fault. And that is about where the earthquake occurred earlier this week. What's kind of interesting about this tectonic region is that large earthquakes are much more common on the North Anatolian Fault, which runs right up here along Anatolia and Eurasia. And as you can see in this figure here, which shows some of the largest earthquakes in the past 120 years, all of the large earthquakes that we've seen, aside from the ones that occurred earlier this week, are on the North Anatolian Fault or on other faults. The East Anatolian Fault doesn't see very many large earthquakes, mostly because the motion that's happening over here is very slow. This plate's only moving at about on the order of like 5 millimeters a year. And so the 7.8 earthquake that was on Monday, and then the 7.5 aftershock, which is also shown in this figure here, were relatively rare for this fault motion. But I think it's worth noting that although these are rare earthquakes, they weren't unexpected. And one way that we can predict shaking from earthquakes is by looking at hazard maps. And so this is a hazard map of Turkey. Shown in the blue here is the East Anatolian Fault. And then this other purple stretch up here is the North Anatolian Fault. And what you'll notice is that both of these locations have about the same hazard. So this means that it has about the same level of shaking that is predicted over a given time period. And so even though this earthquake was rare, it wasn't entirely unexpected. And we do expect about the same hazard along this much slower fault as we do a faster fault in the north. And what I'm going to be talking about today is how observed shaking observations, which is what's shown in this figure on the right, compare to this hazard map. And so in this figure here, we have some maximum seismic intensity data from this earthquake. The warmer colors mean it's stronger shaking. And we want to see how shaking from this earthquake, as well as other earthquakes, compares to what we model in these hazard maps. So to get into the talk today, just to give an outline, I'm going to first start by talking about what are probabilistic seismic hazard maps, how we make them, what they are intended to do, and that sort of a thing. I'll then get into how we assess hazard map performance, how we can use historical data to see what a map should be doing. And then we'll talk about how well maps are currently performing, some of the results to date. I'll also get into what factors we think might contribute to the discrepancies that we see between the maps and historical data. We'll talk about a couple different things that I have outlined here, although there's many other factors that could be at play as well. And then, oops, I forgot to go through this. And then finally, we'll finish out with how these discrepancies can be reduced. So to get started, probabilistic seismic hazard maps forecast a level of shaking that will be exceeded with a certain probability over a given return period. So what's really important to take away from that is that these are not predicting maximum shaking. There is an assumption that is built into the maps that the shaking that is plotted on a map like this will be exceeded by some rate over some given period of time. So for instance, on this seismic hazard map, it has a 2% probability of exceedance in 50 years, which means that 2% of any of these sites are expected to have shaking stronger than what's mapped here within the next 50 years. These maps can be shown as seismic intensity. They can also be shown as acceleration or velocity of the ground motion, and they can be represented in different periods of shaking. These are critical for earthquake hazard assessment and also risk reduction. The way that we build these maps is we use assumptions about the rates, the locations, and the magnitudes of potential future earthquakes. And then we use ground motion models to extrapolate the shaking from those potential events. Hazard curves are then computed for each site. And this is basically the sum probability over all possible scenarios of exceeding a specific ground motion level. And then what we can do is when we plot a hazard curve like this, so in this figure here, we have the peak ground acceleration plotted along the x-axis, and we have the annual hazard, which is also the reciprocal of the return period, where a return period is basically representing the shaking that's expected on average once every return period. So here we have 475 years. PGA for this return period would be expected about once every 475 years. And then we can plot the hazard curve, and where it intersects that horizontal line, that's the reciprocal of the return period, is the predicted ground motion at that site. And then what we do is we make hazard curves for all sites that are within a study region, and we can put those together, and that makes the hazard map. Now, this is not something that is unique to seismology. It's very similar to what is used to make hazard maps or hazard forecasts in other fields. And so here is just a plot of a recurrence interval of floods and the peak discharge. So as you can see, the larger floods happen more rarely. And so we can use the recurrence intervals and sizes of earthquakes to predict future shaking patterns, similar to how they use the recurrence intervals and sizes of floods to predict future flood patterns. And so it's a very common tactic. It's not something unique to seismology. It's similar to other fields as well. One thing to note is that we want these maps to be as accurate as possible. These hazard maps are used directly to influence building codes worldwide. And obviously, it's not difficult to see that too weak predicted shaking is a problem, because if we model shaking that's too weak, it can cause buildings to not be built strong enough, and that can cause structure collapse and damage in earthquakes. That's obviously a problem. But on the flip side, it's a little more subtle, but too strong predicted shaking can also be a problem, because if you have shaking that is too strong for an area, it drives up the cost of construction and expensive buildings don't get built. or buildings that are unsafe don't get retrofitted if the costs are too high. So ultimately, this is something where billions of dollars and countless human lives are at stake to understand exactly how well these maps are performing and how we can make them as accurate as possible. So let's get into like how these maps are supposed to model the probability of shaking. So these maps are supposed to predict the probability of shaking over any given time period, which we'll refer to as little t. So basically it gets kind of mathy here, but at any point on the map, the probability, which we're going to say is little p, that during little t years of observations, shaking will exceed the value on the map with a big T year return period is assumed to be the exponential CDF, which is given right here. So what exactly this means is if we look at an example of having a 475-year return period map, that's kind of what we looked at with the hazard curve figure a couple slides ago. And we wanted to see what the probability of exceeding that value would be in an observation time of 50 years, which is kind of a common lifespan of a building age. What we do, we can plug in little t as 50, big T as 475, and that would back out that this map would have a 10% probability of exceeding at any given point in that 50 years. So this would be a P of 0.1. When we have an observation time that's equal to the return period, the probability is 63%. And so P increases as we have greater observation times relative to the return period. And here is just a map of a hazard map that would have an example of having a 10% probability of exceedance in 50 years. Now, how should these maps compare to observed shaking? Well, it's assumed that if the map is doing well, then the fraction of sites, which we'll call little f, where observed shaking exceeds the map value, should behave the same way as P. And so we ideally want F to be about equal to P. That means that the number of sites that are exceeding the map value is equal to what we would expect the number of sites exceeding the map value to be. If we look at this plot down here, we have predicted shaking along the x-axis and observed shaking along the y-axis. And F is really looking at the fraction of sites that fall above this one-to-one line. So if everything was exactly equal, it'd be falling along this one-to-one line, but like we don't want that. We want a certain number to be falling above. And so F is the number that's falling above this one-to-one line. And P would then indicate how many should fall above this one-to-one line. Again, this is just very similar to forecasts that are done in other fields. So for instance, weather forecasts are evaluated to assess how well their predictions matched what occurred. So this plot is very similar to that one that we just saw, where we have a forecasted probability of rain plotted against the actual frequency of rain. And when we get to situations where the forecasted probability of rain is higher than what was actually observed, then we start to have misfits, and then we can use these misfits to identify biases within the maps. And this is very similar to what we're doing with hazard maps. What's interesting is that even ideal hazard maps are unlikely to perfectly predict shaking. And so there was a study done where they took 10,000 earthquake shaking history simulations, and they compared those to the corresponding schematic hazard map. So it's the ideal map for these shaking simulations. And what was found is that there is considerable scatter in the observed fractional exceedances, and that arises by chance due to where and when earthquakes happen and the variability of shaking. So if we look at this figure here, the blue line is the hazard map prediction, and these little red diamonds inside of here are what the simulation means of observed fractional exceedances, and those well follow the blue line, but there's quite a bit of scatter, particularly at low observation times. And this scatter decreases as you have longer observation times, because as you increase the time window that you're looking at, the largest earthquakes and thus the strongest shaking are increasingly likely to have occurred. So what this study tells us is that longer data sets are better for assessing hazard map performance. Now, this poses a little bit of a problem because we know that long data sets are better, but there's a really short amount of time since hazard maps began to be made. And that's challenging because we can't compare, like, say, 2 decades worth of earthquake shaking data to a 400-year return period map. There's just not enough time to really assess how those maps work. So because of that, we use a method called hindcasting, where we look back at data over hundreds of years and compare those to the maps. And the idea is that if the map well hindcasts, then it should well cast. So hindcasts offer longer records. They're not considered true tests because they're comparing the maps to data that were available when the map was made. But the intensity data or the shaking data were not used directly in making the map. Rather, the magnitudes and the locations of those is what was used in making the maps. So the comparison still gives useful insight to identify strengths and weaknesses and make improvements to maps. And once again, very similar, hindcasting analyses are also used in meteorology and other natural hazards areas. Now, before we get further, I want to make a key point that there are kind of two ways to describe ground shaking. One is peak ground acceleration, also velocity, but we'll focus on peak ground acceleration here, which is called PGA, and another is intensity. And these two things are related, but they're not exactly the same. So peak ground acceleration, or PGA, is the maximum acceleration of the ground as recorded by seismic instruments. So it's much more like physical in a sense. Intensity refers to the effects of shaking on man-made structures and items within them as described by humans. And the reason that these two things really come into play is because PGA is used for most hazard maps. The reason why is because it's directly relevant for engineering purposes. You can use the acceleration of the ground to know how strong you need to build a building to counteract the acceleration. However, most of the data that we have is intensity data because we've had human records that can record what's happened in an earthquake, and those go back much farther than seismic instrument records, which only go back maybe 50 years or so. And so these two things I'll be talking about throughout this talk, and it's just important to know the difference between them and that they're related. Obviously, a stronger acceleration probably is going to correlate to a stronger intensity, but they're not exactly the same. And I'll get into that towards the end. So to look at how California seismic hazard maps perform, we built the California Historical Intensity Mapping Project, which is otherwise known as CHIMP. And it's the first systematic compilation of observed maximum shaking intensities for California. So we collected seismic intensity data from the largest earthquakes in California over the past 162 years. There's 62 total earthquakes, most of which have a magnitude greater than 6. And the data are measured on the modified Mercalli intensity or MMI scale. Then this data set was used to assess the performance of two 2018 USGS seismic hazard maps. And the locations are plotted in this figure here with the circles associated to the size of the earthquake. Now, the way that we built this data set is we took observations of shaking and we assigned them to numerical values on this MMI scale. So for instance, we could take a record like this, which obviously this is intensity, so this is described by humans, and we can infer how strong the ground motion is based on some key things here. So for instance, in this particular record, what you notice is that we see rattling windows, the house is creaking, the hanging objects are swinging, and small objects are overturning. And we would assign that to an MMI of 5. 5 is pretty indicative of when you start seeing objects fall over. So this intensity scale, it ranges from 1 to 12 and incrementally increases, as you can kind of see in this cartoon here. 3 is kind of just strong enough where you might start thinking, did I feel something? 4 is when things start to sway or windows creak, that sort of a thing. 5 is when you start to see items overturn, and then 6 is when you would start to see actual structural damage, and then it would keep going from there all the way up to 12, which is total devastation. These intensity records can come from many sources, and they did for California. Prior to 1924, we mostly rely on newspaper reports where you can read what was published in certain towns and what they described as being the damage or the strength of the shaking, and then make inferments about how strong the shaking was in that area as it would relate to the intensity scales. From about 1924 to about 1990, the U.S. Coast and Geodetic Survey would systematically send out postcard questionnaires after a large earthquake and then collect those so that people could write down what they experienced during an earthquake. And then they took these questionnaires and they published them into reports. So similar to this one here. And we can use these to make some sort of inferment about how strong the shaking was. And these actually have some intensity values associated in this report. And then post roughly 1990, but sort of really the advent of the internet, the USGS has a survey online called Did You Feel It, or DYFI, where people can go online and fill out a questionnaire about how strong the shaking was that they felt after an earthquake. And it'll ask you things such as, did you feel it, where you were you on the top floor of a building, or were you outside, or anything like that? What happened? Did things fall over? Did things move? And you can fill that out, and then they can use that to figure out how strong the shaking was from this earthquake. As Carol mentioned at the beginning, one other thing that I did early on in grad school is I participated in an oral history project where we received a centennial grant from AGU and traveled to California to interview people and retroactively assign intensities for two big earthquakes, the 1992 Joshua Tree and 1993 Big Pine earthquakes. What was unique about these two earthquakes is that they post-dated those postcard questionnaires, but they really predated the online internet survey. And what was even more interesting, particularly on the Joshua Tree earthquake, is that this one happened only a couple months before the 1992 Landers earthquake, which was a much larger earthquake in the same area. And so reports from this one were pretty sparse. And so we went out to try to fill in some of that gap, and we got to interview people who remembered these events. And in particular, these two pictures here are from a woman who came and spoke to us, and her house was pretty much directly on the epicenter of this earthquake and had a lot of damage. So much so, her name was Lupe, and her friends referred to this earthquake as Lupe's earthquake, even 30 years later. And so she came with this big scrapbook of all these pictures, and she had newspaper articles. She had cards, sympathy cards from friends after the earthquake. And it was kind of just a treasure trove of intensity data that she was able to bring. And then we also heard from other people as well. So when we compared the 2018 hazard maps to chimp data, what we found is that the hazard maps are over predicting shaking relative to what we recorded in chimp. So based on the metrics of the hazard map, the return period of this particular one that's plotted here, we would expect that 30% of these dots, where these dots are individual sites, would fall above this one-to-one line here. That's from that equation that I showed back at the beginning. However, when we actually look at the data, we find that only about 6% of these dots fall above this one-to-one line. So once again, along the x-axis is the predicted intensities, and along the y-axis is what was observed. So one way that we could shift the points to be above the line essentially would be if the predicted shaking was lower, then more points would fall above this one-to-one line. And so that's kind of what's indicating to us that the map is predicting shaking that's too strong for this particular data set. And what's interesting is that this apparent hazard map prediction overprediction appears to be a global phenomenon. And so when we look at historical data sets that have been compiled for different countries by different research groups, they're all showing shaking that's less than what was predicted by the hazard map. So shown in this plot here, we have the Central Eastern United States maps. We also have these two California maps that we looked at. There are maps for Italy, which are in red, Japan in pink, France in blue, and Nepal in gray. And we would have expected, based on the 10,000 earthquake shaking history simulations, that we would have these points fall both above and below this line here. This line is representing P, and the y-axis is representing F. And then this is just the observation time over the return period. However, the fact that all these points are falling below this line indicates to us that there might be something going on in how these maps are made or assessed that's causing some issues. Another way that we can think about this is we can look at the ratio of the observed fractional exceedances to the predicted. So this would be the ratio of F over P. And ideally, this ratio would be 1. That would mean that F equals P, the map's doing what it's supposed to be doing. However, when we look at these ratios, we see that most of these fall below 1, and some even fall quite below 1. And so the way that we could think of this ratio as it could be thought of as a decrease in the seismicity rate that would bring predictions into alignment with observations. So what that would mean, if we look at this particular yellow point that's right here, it means that you would have to decrease the frequency of earthquakes by half in order for the current metrics to come into alignment. And we think that that's pretty unlikely. It's not likely that we're that off in earthquake occurrence intervals. And so there's probably something else going on that's a little bit more intricate into the hazard models. Oops. So that gets into what I've been looking at, which is asking the question of why do these California seismic hazard maps specifically predict higher shaking than what we find in CHIP? And there's kind of 3 main ways that we've looked at that could be causing this discrepancy. The first, at its most basic form, is that there might be a problem with the maps. What basically could be going on is that the predicted ground motion might not be the most accurate thing. And so we looked at that by something called site effects, which I'll get into next. The second thing we looked at is whether there might be something wrong with the data that we're using. Basically, it might not be accounting for all of the shaking that we saw in this time period. And so I'll get into that in a little bit. And then finally, there might be a problem with the comparison. So as I talked about earlier, we have these 2 kind of different units of ground shaking. We have peak ground acceleration and we have intensity. And we know that these 2 things are related. And so there are equations we can use to map one to the other. But there might be a bias going on in those equations that's causing things to not work well in this comparison. There's also likely other factors that could be at play, but I'll be focusing on these 3 ones that are colored throughout the remainder of this talk. And basically, what's happening here is if we have observed data plotted as these yellow points, and we have this hazard curve, which is similar to the hazard curve we saw at the beginning as this red line, we can do different things to shift this hazard curve so it comes into alignment with these observed data points, and then the map would be doing what it's supposed to be doing. So to get started, we'll first focus on looking at whether there might be a problem with the maps. And the way that we looked at that is by looking at site effects. So how do site effects change the shaking? At the simplest level, a soft sediment increases ground motion. And so it would kind of be like taking a bowl of Jell-O and shaking it and comparing that to a rock. If you shake a rock, it's not really going to change the shaking that's happening on the surface. But obviously, if you imagine shaking a bowl of Jell-O, it's going to make stuff shake a lot more. However, in recent years, it's become more clear that that is actually, it's much more complicated of a situation than just shaking a bowl of Jell-O versus shaking a rock. And you can kind of think about it more as the difference between shaking a rock versus shaking a sandbox. And so once you reach a certain strength of shaking, when you're shaking that sandbox, some of the energy is going to go into moving grain particles rather than just increasing amplification of shaking. And so that's going to be a key kind of thing that comes in with the next couple slides that I'll show. So we asked the question of whether this discrepancy between the hazard maps and the data are due to exclusion of site effects. So there's one metric that's used commonly to account for site conditions called VS30. It's the shear wave velocity in the top 30 meters of soil. And this parameter has been known to amplify or de-amplify shaking. Now, the hazard maps that were used in prior studies use a uniform VS30 of 760 meters per second across the entire state. That would basically be like assuming that the entire state of California was on bedrock. The actual VS30 varies quite considerably throughout the state, as you can see in this figure here. And sites in sedimentary basins like the San Francisco Bay or the Central Valley or the Los Angeles Basin all have VS30s that are quite a bit lower than 760. And so we wondered if those lower regions might have stronger shaking that would then cause the discrepancy between the maps and the data. So what we did is we took the ground motion models that were used to create the maps and we approximated what would happen if we put site effects into them. What we found is that the resulting amplifications are dependent on VS30, the period of shaking, and the strength of shaking. So when we have a low VS30, and a weak short period shaking, we see linear amplification. This would kind of be like shaking that bowl of Jello. However, once we have a low VS30 and shaking that is strong enough, we actually see a de-amplification. So this would mean that shaking would actually be weaker than what it would be on a 760 meters per second ground condition, so like a bedrock. And the reason why that happens is because of like the sandbox, some energy goes into moving the grain particles. It's called soil damping. And so what can happen is that nonlinear effect can actually offset any linear amplification, causing a net decrease of shaking at softer sites. So because of that nonlinear effect, when we put side effects into the hazard maps, we found that it actually made a little difference. You can see in these two maps, this one is the original map, and then this one here includes side effects. There's really no difference between the two maps. It's both visually and then also analytically, there's hardly any difference at all. And any small differences are due to the nonlinear de-amplification offsetting that linear amplification at the periods that are relevant to intensity. Now, the next thing that we looked at is whether the discrepancy was due to a problem with the data that we were using. And so the reason that this comes into play is because hazard maps are built with the assumption that they are modeling shaking from all earthquakes with a magnitude greater than about 5 for California. However, when we were building the CHIMP data set, we looked at mostly earthquakes greater than a magnitude of about 6. And so there was a question as to whether we were missing earthquakes between magnitudes 5 and 6 that were causing shaking that would be relevant to this analysis, but that weren't included in the data set. So what we did is we recalculated the hazard by removing or approximating what would be removed if we took out the hazard from magnitudes between 5 and 6. So what that would basically do is we were taking the original hazard curve and we're taking some of the hazard out of it by removing anything that came from a magnitude 5 or 6, which would then bring this curve lower and decrease the predicted PGA. What we found is that the reduction in PGA was about 10% near major faults, like the San Andreas right over here, and up to 35% in more background zones. So doing this analysis overall, we found that this is part of the problem. It reduced the discrepancy between the observed and predicted shaking, but it didn't reduce it enough that this was the only problem. So this is a little bit of it. We do need to have consistent data sets to the hazard maps in terms of what events we're looking at, but there's something else going on. It's not just this. So what we think actually is probably one of the biggest contributors to the discrepancy are these equations that we use to convert a ground motion to intensity. So as I've said, remember, usually hazard maps are given in peak ground acceleration, whereas the data are in intensity. And so to assess these hazard maps, what we have to do is we have to take the PGA hazard map and convert it to an intensity hazard map using a conversion equation. We call these G-mice. And basically what we're finding is that there are some assumptions that go into these G-mice that are actually not entirely correct. And they cause the G-mice to work well for average intensities and ground motions, but not above average. So if we look at this plot right here, where we're considering some PGA and intensity data that are correlated. So like at this site for this earthquake, we had a PGA of this and an intensity of this. It's a data set that has both. We can look at the pink points here, which represent the average for a given earthquake with a varying distance, and these green points are above average shaking. So what you'll notice is that the black line, which is the G-mice, it well follows the average, but it overestimates above average ground motions. And so the reason ultimately that the G-mice are seeming to work well is because they're both correlated with magnitude and distance, but they're not completely related. PGA and MMI are not completely causal with each other. And this has been assumed previously and is an incorrect assumption. So for instance, if we had, let's say that we had this particular dot here, which is a PGA of about 100 centimeters per second squared, sorry. And let's say that it came from a magnitude 5 earthquake at 100 kilometers, and we can see that that was an above average ground motion for this particular event. So based on that, it would correspond to an intensity of about 3 based on the data here. However, the GMICE equations would map it up to an intensity 5. So you can see that if we have a hazard map that is above average, which most hazard maps map above average ground motion because it's, what is expected to be exceeded in a certain period of time, that these equations are going to map that value even higher than what it should be. And so this could be contributing to why the hazard maps are higher than what we think. Basically, this is, I know it's kind of a statistics heavy sort of project right here, but it's ultimately an issue of correlation versus causation. Intensity, or MMI, and PGA are both causal with the magnitude and distance that caused that shaking, but they're only partially correlated with each other. And previously, it's been assumed that these also are causal with each other, but we're finding that that's just not the case. And so that's causing some issues in the comparison between hazard maps and intensity data. And so that's something that we're working on at the moment to improve these equations and reduce that bias so that these assessments are more appropriate. So just to summarize the results, what we found by looking at the comparisons of hazard maps and historic shaking data is that the maps are predicting shaking higher than what's been observed. And when we look into why that's the case, we find that side effects don't explain the overprediction. They really make hardly any difference because of that nonlinear de-amplification. And actually, I didn't really get into this, but actually predicted shaking is ever so slightly amplified at most sites, which increases the overprediction very slightly. So side effects are not a cause as to why these maps are not performing as expected. We find that the minimum magnitude of CHIMP does explain the overprediction a little bit. It reduces it, but it doesn't fully eliminate it. So it doesn't fully explain that overprediction. And we think that these GMICE, these conversion equations, or otherwise the method that we're using to compare the data to the maps seem to be a major effect. But we think that other things beyond even what I've talked about here likely play some role as well. So thank you. I'll take any questions if anyone has any.
Thank you. Are there any questions? Any questions for Molly? Okay, I have one question. Assuming this overprediction was corrected, how much would it really save in terms of building costs?
Yeah, that's a good question. What we're finding at the moment is that this overprediction is on the order of about like an intensity unit. And so kind of for context, that that might be the difference between shaking where items just fall over versus like they're actually being structure damage. And I'm not exactly sure how much that maps into acceleration, which is what would be relevant for building codes. But it's, I mean, ultimately, I think, we want to try to understand exactly what's going on in these hazard models. And we do want to try to make the hazard models as accurate as possible. So I'm not exactly sure how much this would change, the building codes or anything that would actually be relevant to how buildings like survive shaking. But I do think that it's an important intellectual question as to how well these models are working, but also, we do want these to be working as best as possible because this is, observed worldwide. So it matters for, especially regions that, cost of production might be more limited. Yeah, so kind of scared of the question there, I guess, a little bit, but that's what I would say.
So I would like to follow up.
Mm-hmm.
Sorry, I didn't raise my hand officially. On Carol's question, so it seems like these hazard maps are also used for insurance purposes, correct?
Absolutely.
So is the insurance industry, are they interested in your work or?
That's a good question, I guess. At least one other student that's close in my they graduated when I started. He went on to work for a reinsurance company. So absolutely, like hazard models are very practical in insurance industries. I haven't secured a job yet, but insurance wouldn't be out of the question for that either. Yeah.
Thank you.
Mhm. Thank you.
Any other questions?
I just out of curiosity, I'll just jump in here for a moment. So our speaker last week said she would not move to the Pacific Northwest
Hmm.
because of the risks there. So are you more sanguine about that? And I'll ask in a local area, how about the New Madrid fault zone? Do you think we've overestimated the risks there?
Oh, so regarding the Pacific Northwest, I go like a little bit back and forth on that, because on one side, there obviously is a massive tectonic zone going on there. But on the other hand, we don't know like when that large earthquake might happen. We know that it will, but we don't know when. And so it is kind of a question of, do you control your life for an event that might not even happen in your lifetime? And I don't know exactly my thoughts on that one, but I think it's it's there's no way we know whether it's happening in the next 100 or 200 years. We don't really know. Regarding New Madrid, my understanding on that one is that there also isn't too much movement going on there. But once again, do we make choices based on something that may or may not rupture again anytime soon? So yeah, kind of to both of those questions. I guess it's ultimately, it's kind of, I feel like it's a little bit of a philosophical question in a way as to whether that's personally something that bothers you or not.
But the question is,
kind of
would you move to the Northwest, Pacific Northwest if a job was available? And if so, what would you do?
I think I would. Or let me say this, I don't think I wouldn't because of the seismic hazard there. I don't think that would be the determining factor or not. But I think that if I did, I would, just probably like do the best to find a place that seems to have, seismic retrofitting or something. Or if I owned a house, I would invest in the money for seismic retrofitting for that house if it wasn't already retrofitted. And then I think I probably would just try not to think about it too much, honestly.
Any other questions? Sorry, go ahead, Stephanie.
I'll just share a comment because those questions reminded me of, I think, Suzanne Vanderlee, who's a seismologist at Northwestern. She was being interviewed on WTTW a couple of years ago after a couple of the California earthquakes. And they asked her, would you move to California? She was very clear. So, of course, they have great weather.
Yeah, that's true. That's true too. Pacific Northwest, I guess, is a little bit more, it can be a little more murky, but yeah, I agree.
Yeah. But Molly, this was really.
Oh, excuse me, just one thing. Could you turn off the screen sharing, Molly?
Oh, yes. Yeah.
Yeah. Molly, this was really great work. It was very cool how you did some of the qualitative research with the interviews and then a lot of statistical analysis as well. I was going to ask too, because last week we just had like a geodesist here, and now you're a seismologist, and I'm wondering, have there been, are any of the hazard maps like combining both of those data sets or?
Yeah. Well, first of all, thank you very much for those kind of words. But yes, so we can use information about, how plates are moving, how fast they're moving, to